All right, guys, I wanted to start with a little bit more advanced naming of alkanes. We already talked a little bit about some of the basic rules, trying to sort out what the longest chain of the alkane is, identifying the substituents and where they're located, in other words, numbering it. We decided that when we number the chain, we have to number in the direction that gets us to a substituent the fastest. If there's ties to be broken, then we other ways to number it, then we would number it in the way that gets us to the next substituent the fastest. But remember, there's only a hierarchy of rules, and the first rule is the most important rule. So in other words, even if you get a substituent at 2 and 7, it's better than having a substituent at 3 and 6 or whatever like that. So at the end of the day, there's going to be a lot of different examples. It's going to get a lot more complicated. And at the end, also in organic chemistry, it's really easy to come up with an example where you just really get stuck with and you don't know what to do. There are a book of rules about how to name compounds, and there's so many different types of compounds. It's really not appropriate to dig real deep into all of that possibility in an organic chemistry class in your sophomore year. So let's get into some more complicated examples, and then we'll go from there. All right. So I'm going to start just drawing a couple of random examples. And we'll see what happens here. Because one of the things that we haven't talked about yet is what do we do when a substituent itself has a substituent? And so that's going to present some challenges for us. And so what I want to do is I want to start off by doing the same thing that we did before, which was identify the longest chain of carbons. So in this molecule, I created it on purpose the way it is to illustrate a couple of different rules. One of the rules is what happens if we start to get more complex substituents. And another one is what if there's more than one way to number the longest chain? So let's take a look at this, and let's think about this. Here's the first common mistake. Students say, well, I want to find the longest chain. This looks like the longest chain here, 6 carbons long, and so I'm going to go with that. Remember, the longest chain isn't necessarily presented to you left and right. It could be presented to you up and down, or it can be some other combination. Right now, what it looks like is that I could go 1, 2, 3, 4, 5, 6, 7. So that chain is longer than 6, so that one would be one of the possibilities. Let's try something else, though. Let's think about if I went 5, 6, 7. Oh, there's 2 different possible 7 carbon chains. Remember, going 7 down here is the same as going 7 the other way, so I won't even with the two blue 7s, so I won't even mention that particular version, but these 2 7s are equivalent. So let's take a look at that. So let's try something else. Let's go 1, 2, 3, 4, 5. Oh, that's actually the exact same chain. 1, 2, 3, 4, 5. If we get back here, that's 6. So it looks like the longest chain is 7. But now the question is which 7 is the appropriate chain? So this brings us to another rule. If you have 2 chains of the same length, then the first thing to do is pick the chain with the most substituents. And the reason that we pick the chain with the most substituents is it ends up being, the substituents end up being less complex. So if I pick the red chain, this ends up being a substituent, and that substituent in itself has a substituent. And we'll deal with that in a second, because there's sometimes when you can't possibly avoid that. But in order to minimize that situation, you pick the direction that has the most substituents. And so the red chain would have 1, 2, 3 substituents, and the blue chain would have 1, 2, 3, 4 substituents. So we'll pick the blue chain. We'll number it in the 7 carbon chain that ended with the blue numbers. Now the question is, do we start here or do we start here? And that's something that we're going to have to sort out based on our previous rule. Again, we'll number in the direction that gets us to the first substituent as fast as possible. And if I number in this direction, 1, 2, 3, 4, 5, 6, 7, then that gets me to a substituent at the first position or the second position, rather than the substituent at the third position, which would be numbering the other direction. All right, so now that we've done that, we know that it's a heptane. Now we want to identify the substituents. I got one there, this one here, and this one here. And so that means that I have a diethyl and I have a dimethyl substituent. The ethyl groups are located at 3 and 4, and the methyl groups are located at 2 and 5. So these are the two sets of substituents that I have to deal with, and I have to attach them to the name heptane in order to sort this out. How do we do that? Well, we put the names in there, we put the names in there alphabetically. Now, I could say, well, they both start with D. And this brings us to another rule. We don't use di, tri, tetra, etc. in alphabetizing except when they are in parentheses. And we're going to talk about when they appear in parentheses in a second. In this example, they won't. So I don't use the D and di to alphabetize. I use the E versus the M. So when we have multiple substituents, we typically alphabetize them. So an ethyl would become before a methyl, a propyl would come after a methyl, etc., whatever the case may be. If it was a chloro group or a bromo group, you would alphabetize them appropriately as well. So in this case, the methyl group comes after the ethyl group. And so the way that I sort this out would be to put 3, 4 diethyl, more hyphens, 2, 5 dimethyl heptane. And so this is the name of this molecule, the way that I've drawn it out here. And so that illustrates a couple of other rules. If you have 2 chains that are the same length, then we pick the chain that has the most substituents. And if we need to alphabetize substituents, we do alphabetizing based on the parent name, not the numerical prefix, unless those numerical prefixes are presented to the reader inside of a parentheses. And so let's take a look at when that might happen. And so let's come up with a different example. So bear with me a second while I make an example. And I wanted this to be straightforward. So it is clear to me that the longest chain is going to go straight across. It's 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. If I check, I have some other chains, but the longest they get are 8 carbons. And so the longest chain is 9 carbons. It is the one that's straight across. So let's ask ourselves this: which way should I number the 9 carbons, from left to right or right to left? Well, we should see that I number from right to left because I get to a substituent at the 3rd position rather than at the 4th position. All right, so now that I've not done this, I know that it's some sort of non-ane. So let's identify the substituents. I've got one there, I've got one there, I've got one there, and I've got one there. Well, let's do the easy one. I've got a 4,5-dimethyl that I have to deal with. There's a methyl group at the 4 position, a methyl group at the 5 position. So I'm going to put them together and say dimethyl. But these other 2 substituents that are circled and that I have arrows pointing to are a little bit more complicated. And so we have to sort those out. These are complex substituents. And so how do we deal with a complex substituent? Well, if we look at these substituents, we see that that we can say that they are substituents that themselves have substituents. So how do we do this? We're going to re-invoke all of the same rules that we've done up to this point. Up to this point, we've said we're going to pick the longest chain, we're going to identify the substituents, and then we're going to number the chain, and then we're going to tell the reader where the substituents are. But at the end of the day, we're going to apply all these same rules to more complex substituents. And so let's take a look at the one at the bottom, this one here. If I were to say, okay, what is this substituent? I would say, let's find the longest chain. And I've got 2 red dots here, 1, 2. That's as many carbons in a chain, not including the carbon that is already attached to the main chain. Remember, we've already counted the carbon in blue because it's part of the main chain. It's one of the 9 carbons in the nonane. So the 2 red carbons represent the longest chain of carbons directly attached to the 9. And so then what do we say about that? Well, remember, that's a 2-carbon chain is an ethyl group. So that at that position, we have an ethyl group. Oop, spelled it wrong. All right, but what is attached to that ethyl group? The ethyl group has its own substituent. There is a single carbon attached to it. So that's a methyl group. So what we're going to say is that the group that we have attached there at the 3rd position along the nonane is a methyl ethyl group. But just like you would do with other substituents, you need to tell the reader where that methyl group is attached to this side chain. And the way we would number side chains is we would tell the reader, we start by numbering them as close to the main chain as possible. So this carbon always would be carbon number 1. Further out would be carbon number 2. And so when we put it all together, the group is 1-methyl ethyl. And some folks might be saying, well, isn't that an isopropyl group? Well, it turns out it is an isopropyl group as well. But what we mean by isopropyl is that this name is actually a common name. It's a common name that is in such great use that it's accepted by IUPAC as being an acceptable naming convention in addition to the systematic version, which is 1-methyl-ethyl. There are plenty of these groups that you should become familiar with. Isopropyl is one of them. This is an isopropyl group connected to a main chain. Another one you might want to become familiar with is the one that I have shown in the other bubble. This would be a T-butyl group. Another one is sec-butyl. And you can look up common alkyl substituent names in your book and try to be familiar with them, because the language out there in the internet, the language out there, another chemist, it is pretty common to use these names. However, for me personally, I'm always going to refer to the systematic name, because it's just going to reinforce the ideas of how we name these compounds. So isopropyl is okay. It does change how you alphabetize. You start with an I. It does change how you alphabetize with these other things, because you would either choose T or you would choose B or B in these cases, and not the S or the T. And so that starts to get confusing. And so I always just use the common names. The systematic names. So I'm going to get rid of the common names for now so that they're not an additional bit of confusion. And let's go back to the name of this group, the 1-methyl-ethyl group. So this is the name of this complex substituent. And what I want to do is I want to tell the reader where that complex substituent is located along the chain. So it is at the 3 position in the longest chain from the main parent group, the nonane. And so I would put all of the name of that complex substituent, the 1-methyl-ethyl group, put it in parentheses, and then number it just like I would any other group, just like I did the dimethyl group above it. All right, so let's do the same thing with this other group. I'm going to count the longest chain that is connected to the main carbon chain. 1, 2. So this is also an ethyl group. But in this case, I have 2 substituents on this ethyl group. 1, 2, and they're both methyl groups. So it's a dimethyl-ethyl. In fact, it's 1,1-dimethyl-ethyl. Now, some folks are going to say you don't need the 1,1 because it's implied. It's the only way that it can happen. I think that's correct. But what I want to do is I want to maintain, it's not wrong to include the numbers. So I want to include the numbers just to maintain a level of consistency in how we do the naming. And so this substituent is 1,1-dimethyl-ethyl. And where is it? It's at the 6th position. And so so now we have our substituents. We have them all named. And so let's put them together. And remember, we're going to put them together alphabetically. Just like I said before in this previous bit of naming, we would normally not use di, tri, tetra, or any of those prefixes to do alphabetizing, except we do when they appear inside of parentheses. And so here's an example of when that appears inside of a parentheses. So we're going to use M, and D for alphabetizing. So this one gets first. It's 6,1,1-dimethyl-ethyl. That's the first one. So now which one is next? This one or this one? Well, it goes methyl, M-E-T-H-Y-L. So does this one, M-E-T-H-Y-L. But then there's some other letters after methyl. So this one comes first. This one would be the next one in the dictionary. So it's 4, 5. Dimethyl. 3, 1 methyl ethyl. Now close the parentheses, but no other breaks. Non-ane. And so you see, with even a molecule that has, you know, a few and it does have 9, 10, 11, 12, 13, 14, 15, 16, 17, it has 18 total carbons, the name becomes pretty complicated. And so this is an example of something that would be, you know, about as hard as it gets on an exam that's going to first test you on your ability to do this naming. But at the end of the day, this is an example that kind of brings in all the rules together. Number the longest chain, or identify the longest chain, then number it in the direction that gets you to a substituent the fastest. If there's a tie, in the longest chain, then number the longest chain that has the most number of substituents. Locate all the different substituents, name them, and put them together alphabetically. This is a summary of the basic ideas of what these rules are. Now, there's a couple of different things that I want to go at before we sign off for the day. What happens if I have a cyclic group? Well, this is a 6-carbon molecule, and it's cyclohexane. What we're going to do later is we're going to talk about how we would name molecules that are a little bit more complex and cyclic. And so we'll figure out how to name something like this. But what I want to do is I want to talk about what would you name something like this. It's got a cyclic group as a substituent. In this case, what you're going to do is you're going to name this based on the number of carbons. Just like here, this is cyclohexane because you have six carbons in a ring. This one would be a cyclopropyl group because it's a substituent off the main chain. So it's at the 2 position, 1, 2, 3, 4, 5, 6. So this would be 2 cyclopropyl hexane. That's the name of this thing. We got an R down here. When you get to a situation where you might have a cyclo group directly connected to another chain like this, this becomes much more complicated. And it's really, at this point, it's not a cyclo group. It's, in other words, it's not a cyclopropyl substituent. You have to then reconsider whether or not the cyclopropyl group is actually the main chain or not. And so that's going to be more complicated, and it's not really appropriate for this discussion at this moment. So let's come up with one last example, and we'll stop there for the night. Okay. All right, so let's try to sort out what the longest chain might be. So I'm going to go through a couple of different possibilities and just make sure that I understand. Start here. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9 carbons as a possibility. Let's try 1, 2, 3, 4, 5, 6, 7, 8. That's 8 carbons as a possibility. Let's try 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10 carbons as a possibility. Let's try 1, 2, 3, 4, 5, 6, 7, 8, 9. That's also 10 carbons as a possibility. Let's try 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10 carbons as a possibility. And so it looks like we have 3 different possibilities that's 10 carbons. Let's do the yellow one that's combined with the blue. And let's do the red one that's combined with the blue. And so let's double count. Yellows, yellow into blue. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Red into blue. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then just the blue chain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, which one is it? Let's double check. Let's take purple and identify the number of substituents. So on the main chain, 1, 2, or on the straight one, 1, 2, 3, 4, 5, 6 substituents. Let's take a different color and let's try this one. So if we use the yellow one, it would be 1, 2, 3, 4, 5 substituents. That's not as many. And let's try the red one. Let's try the red one. 1, 2, 3, 4, 5. So it looks like the longest chain is going to be 10 carbons, and it's going to look like the 10 carbon chain that's the longest is going to be the one that's kind of straight across, because it should have 6 substituents if we counted right. 1, 2, 3, 4, 5, 6. So indeed, it is 6 substituents. And so the carbons marked in brown will be the main chain. It is 10 carbons long, and so it's a decane. All right, let's sort out each of the substituents. Which direction do I number from? Do I number from this end or this end? If I take a look at the left side, I get to the chlorine group at the 2nd position. If I take a look at the right side, I would get to the methyl group at the 3rd position. So when I'm numbering the chain, I'll number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll number it this way so that I start with the group in the 2nd position. So let's identify everything. I've already said that I've got the chlorine group in the 2nd position, so that's a chloro group. It could be a bromo, an iodo, a fluoro. So it's in the 2nd position, so it's a 2-chloro. Let's keep moving down the road. I've got a 3-ethyl. It's 2 carbons long. Then what do I have? Let's take a look at 4. What do I have? 1, 2, 3 carbons is the longest, and it's got a methyl group at that 1st carbon. It looks like the same thing is happening at the 5th position. I've got 1, 2, 3 carbons, and it's got a methyl group at the 1st position. So what is that? That is a propyl group because it's 3 carbons long. It's a methyl propyl group because it's got the methyl group off the 1st carbon. So that makes it a 1-methyl propyl group. But I have 2 of them. And the 2, so that means it's a di 1-methyl propyl group, and the di would come outside the parentheses because you're telling the reader that there's 2 of these groups coming off the main chain. And so they're both located at the 4, 5 position. And so I kind of scrunched that up. And so let me just erase that and I'll rewrite it so that it's not confusing. I would have 4, 5 di 1-methyl propyl as the 2 groups there. And then it looks like I have a 6, 8 dimethyl. And so let's put it all together. What does the alphabetizing look like? Well, it looks like C comes first, then E. This di comes outside the parentheses, so this is M. This di comes outside of her parentheses, so it's also M. This is methyl with nothing after it. This is methyl propyl, so it would come last. So this would come first. This would come second. This would come third. And this would come fourth in order of alphabetizing the substituents. And so let's put it all together. So it's 2-chloro, 3-ethyl, 4,5-di, 1-methyl-propyl, oh, that came, I'm sorry, that's the last one. So it's 3-ethyl, 6,8 dimethyl, 4,5 di, 1-methyl propyl, decane. There it is. So it gets complicated really quickly. So not only are you going to be able, not only are you going to have to be able to take a picture and name it, you're going to have to be able to take a name and you're going to have to be able to draw it. So let's take a look at something like this. Let's take a look at 3-bromo, 4-methyl octane. So if I give you a name, you also have to be able to draw it. In my opinion, it is almost infinitely easier to go from a name like 3-bromo, 4-methyl octane backwards into the picture, because all of the groups are already laid out for you and all you have to do is start to draw them. Well, you know it's an octane. It doesn't matter to you whether or not the picture was messed up or the octane went straight up and down or the octane went left or right, because when you draw it, you get to pick how it's drawn. So for simplicity's sake, let's draw octane straight left and right. Again, it doesn't matter which direction you start drawing it from, you get to pick since you're drawing the molecule. So we read left to right, so let's draw left to right. 1, 2, 3, bromo, 4, methyl octane. So it is much easier to put together a picture than it is to go from a picture to a name. But at the end of the day, you have to be able to do it both ways. And so this is the end of alkane naming when it comes to the first part of organic chemistry. You're going to eventually have to take this same naming and we're going to have to deal with cycloalkanes. And then we're going to have to deal with alkenes. And then we're going to have to deal with alkynes. And eventually we're going to, before we do some of that, right after cycloalkanes, we'll have to deal with different versions of what would essentially be the same molecule. And so we've got in this picture, we've got a methyl group at the third position along a hexane chain, but one of the methyl groups points towards you, one of the methyl groups points away from you. You find that these are actually different molecules, and so they have to be named accordingly. So naming starts to become a lot more complicated. It's already very complicated as it is. We're going to start to throw double bonds at you, triple bonds at you, and we're going to start to throw differences in three-dimensional arrangements at you as well. So it's important, it really is important to learn how to do this basic naming. I call the basic naming the low-hanging fruit on an exam. Most community college and most college professors in an organic chemistry class will assess you on your ability to name molecules. And it's one of the easiest things that you can do in organic chemistry. It's a set of rules, it's systematic, and you don't really have to know much about chemistry in order to do naming. So I get a lot of students that miss questions on exams and quizzes about naming all the time because they they don't practice, because it does seem easy at first, but until you practice putting the rules uh, uh, until you get the rules into practice, it's easy to skip and miss things. And so it's not unusual for there to be 15 or 20% on an exam or quiz associated with just naming and drawing pictures from names. But students don't practice that because it appears simple at the first kind of glance. And that's why I wanted to do examples like this to kind of illustrate to you, well, yeah, it does appear simple at first glance. 3-bromo-4-methyl-octane, that's pretty quick, that's pretty simple, but it gets really more challenging really quickly. The molecules get to be a lot more complicated, and it doesn't need a whole lot of atoms in order for that to happen. And so we'll leave it right there. That's the end of alkane naming. What we're going to do after this is we're going to move on to Newman projections, rotations around single bonds. We're going to talk about how the energy changes in those rotations. Then we're going to do cycloalkanes. We'll name cycloalkanes. And then we're going to talk about different projections of cycloalkanes. Specifically, how do we think about the conformation or the shape of cyclohexane? And that'll be the end of chapter 4 before we move on to stereochemistry. And this is the stereochemistry part. All right, have a good one.